Welcome to Lesson 13E, Design of Supersonic Airfoils. In this lesson, we'll discuss the design of supersonic airfoils, for example, why they often are called diamond airfoils. We'll discuss the pressure distribution and how to calculate lift and drag on a diamond airfoil, and we'll look at various angles of attack. First, let's compare subsonic and supersonic airfoil shapes. I'll assume that you're more familiar with subsonic airfoils. At moderate angle of attack, the streamlines will look something like this. For your typical subsonic airfoil, the region above the airfoil has high speed and low pressure, while the region below the airfoil has low speed and high pressure. That's why you get a resulting lift force. What about supersonic airfoils? In general, they're much thinner. In fact, they often have a sharp leading edge rather than a very rounded leading edge like this. A common shape, in fact, looks something like this, and we call this a diamond airfoil. And this is what it would look like at angle of attack. Let's now do a qualitative analysis of a diamond airfoil. I'll start by looking at zero angle of attack. If this is our diamond airfoil, and we'll consider a symmetric shape, top and bottom, with supersonic flow from left to right. Let's discuss what happens. Well, we can think of this line upstream of the leading edge as kind of like a wall, and so this looks like a sudden change in wall angle, which we know will lead to an oblique shock, and the bottom will be symmetric. Now think of flow along this wall, which will be parallel as we go from 1 to 2, but we suddenly see a wall that falls away, which we know will give us an expansion fan, assuming that this Mach number is still greater than 1. That increases the Mach number. M3 is greater than M2, and again it's symmetric at the bottom. But now we encounter a change in wall angle, again upward from this point of view, so we get another oblique shock to 4. Again, symmetric on the bottom. The flow then straightens out for this zero angle of attack case. Let's sketch the pressure in these regions along the walls as a function of distance down the airfoil, which we can call x. Let's let atmospheric local pressure be P1 in region 1, but along the wall when we go across this oblique shock, the pressure suddenly jumps up and stays constant at pressure P2. Through the expansion fan, we know that pressure decreases as Mach number increases, so we suddenly drop down to some low pressure P3. And we're not concerned with P4 here, because I can determine the lift and drag just from these two pressures, P2 and P3. Namely, since pressure always acts normal to a wall, P2 acts something like that, P3 like that, and it's symmetric top to bottom. You can see that the pressure forces on the top and bottom cancel at zero angle of attack, so there's no lift force. But since P2 is bigger than P3, and the way this is angled, we see that the drag force is not zero. And this is a very interesting phenomenon. Even if we ignore friction along the walls, we still have drag. The drag is due to pressure only, not to shear stresses. Of course, in real life, you'll have some friction forces as well. We also sometimes call this wave drag. So in comparison, a 2D incompressible inviscid flow over an airfoil has drag equal to 0, and that's true even if the lift is not 0. That you may remember as D'Alembert's paradox. But for 2D supersonic inviscid flow over an airfoil, we have drag is not 0, even if the lift is 0. This is because of the wave drag. Now let's discuss different angles of attack for this diamond airfoil. I'll resketch a diamond airfoil with delta as the half angle of the diamond shape, and we'll consider 3 different angles of attack. Case A will be when alpha, the angle of attack, is less than delta, as I sketch here. And you can see that there's a slight increase in wall angle, if you think of this as a wall, from the free stream to this leading part of the airfoil. Thus we get an oblique shock from 1 to 2, and then our expansion fan from 2 to 3, followed by another oblique shock from 3 to 4. On the lower side of the airfoil, you can see that the change of wall angle is bigger. At the top of the airfoil, this change of wall angle is delta minus alpha. But at the bottom, and I'm exaggerating delta for illustration, this sudden change in angle is delta plus alpha. So there will be a stronger oblique shock from 1 to this region, which we'll call 5 here. And I'll move this down a little bit to not be so crowded. The flow goes from M1 to some smaller M2, and then to M5 across the bottom oblique shock. And there will be another expansion fan at the bottom, which increases the Mach number to M6 in region 6 and M3 in region 3. Finally, there's another oblique shock at the bottom, but again, these angles are not the same. And what happens is you get something that we call a slipstream, where the speed can be different between region 4 and region 7.
What about the pressure? Does P4 have to equal P7?
Yes, Ozzy, it does. Physics tells us that the pressure has to be the same across this slipstream, and the angle here will adjust itself up or down in order to meet this pressure criterion. And even though these speeds are not the same, they have to be in the same direction.
Thank you.
Note that we're assuming that these oblique shocks are weak, and that the flow downstream of the oblique shocks is still supersonic. Otherwise, you would not have these expansion fans. Let's do a qualitative analysis of the pressures. It turns out that the oblique shock from 1 to 5 is stronger than that from 1 to 2. Therefore, P5 is greater than P2. And similarly, P6 is greater than P3. And because of this, when we look at the geometry, we see that we have greater pressure forces on the bottom than on the top. So we get lift on the airfoil. And this is how a diamond airfoil gets lift at small angle of attack. You have enough information now and all the appropriate equations, if you know the angles, to calculate flow across the oblique shocks and across the expansion fans. The only difficulty is back here, where we don't know this angle of the slipstream. So some iteration is required to solve this. The way I would do that is to guess some angle, calculate flow across each of these oblique shocks, and check the pressures. You iterate the angle until the pressures match, as we said here. Now let's consider case B, where alpha is greater than delta, instead of less than delta as we had with case A. This would be at some medium angle of attack. Let's rotate this to some higher angle of attack this time, such that the flow encounters a downward sudden change in direction at the nose. In this case, we get an expansion fan at the top from 1 to 2, and the Mach number increases with the flow parallel to this wall. On the bottom side, we still encounter a change of wall direction downward like this, so there's still an oblique shock from 1 to 5, and at both of these corners we get expansion fans to regions 3 and 6 respectively, with the flow again always turning parallel to the wall since we're neglecting boundary layers. Finally, we get another slipstream with an oblique shock from 3 to 4, and depending on this slipstream angle, here it looks like there's no change at all. So let me redraw this with a slight angle so that we get a weak expansion fan. But I comment here that depending on the slipstream angle, this can be either an expansion fan or an oblique shock from 6 to 7. Again, you would have to iterate until P4 is equal to P7, even though V4 and V7 would not be the same. This iteration is a little more difficult. What I suggest is assume, for example, that there's an expansion fan, work through the math, but you may not be able to find a slipstream angle such that P4 can equal P7. If that's the case, try an oblique shock instead of an expansion fan, and then iterate the angle here. And you'll find that one of those will give you P4 equal P7, and that would be the correct value. And I realized here I forgot to label alpha. Alpha is the angle of attack, which here is greater than delta. Finally, case C, where alpha is very large compared to delta. This would be a very high angle of attack. Again, we take our diamond airfoil and turn it to a very high angle of attack, alpha being much greater than delta. Well, we'll have an expansion fan here that's trying to turn the flow to the direction of this wall, but you'll reach an angle of attack that's so high that the flow can't handle this, causing the flow to separate. The flow still turns across this expansion fan, but it can't turn such that the angle is parallel to this wall, and so the flow separates, and this becomes very complicated. Finally, I'll mention that this is similar to a sudden wall angle change. For example, at moderate angle change delta, the flow has no trouble turning parallel to the wall. We'll call this the small delta case. There will be some limit, however, at some large delta, where the expansion fan can still turn the flow parallel to the wall. Now consider the case where we have a very large delta, in fact greater than 90 degrees. For some Mach number m1 coming in, we theoretically would get an expansion fan that can actually go below the horizontal. And in the limit, our region 2 would have m2 approaching infinity, since Mach number keeps increasing across this expansion fan, and P2 going to a vacuum, and the flow would turn something like this, approaching some maximum turning angle. But in real life, there are boundary layers along the walls, and those will contribute to flow separation. You won't be able to get infinite Mach number in a vacuum. Instead, the flow will separate at some angle like this. This kind of flow is beyond the scope of this course. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.